Hi, I'm Eric Anderson, President of Basin Precision Machining. I'd like to talk to you about thermal deburring. For those of you who aren't familiar with thermal deburring, I'll get into a little bit of a detailed explanation on it in a minute here, but we make a lot of hydraulic components. And last fall we launched our thermal deburring line to automate the deburring of hydraulic manifolds. Now, when you think about it, the single greatest opportunity for failure for a hydraulic system is loose debris in the system. And the very process that we use to manufacture manifolds for hydraulic systems generates a burr every time we drill a hole into another hole. And that's what a manifold is. It's a series of holes that connect passageways to other passageways. So, like most machine shops in this country, what we've been doing is having a man sit there with a drill and a knife and good dexterity and skill and attention to detail and pick every burr out of parts that can sometimes have 1,200 features. It doesn't sound like a glowing opportunity for success, and it's not. But largely that's how manifolds are deburred in the United States. So we went looking for an automated process, and after a lot of trial and a lot of error, we landed on thermal deburring. We had long ago written thermal deburring off because it was seen as ineffective when we're doing a large volume of different part numbers. Most thermal deburring is dedicated production in the United States, and it involves setting the machine up for one machine and by trial and error getting your ratios right, and then you just thermally deburr that part only. Where we differ is that we're able to do any of 190 part numbers in any order, in any sequence, with very little changeover, like a minute of changeover, and have a successful result on deburring because we're using a technology that is relatively unused in our country. We went to ATL, which is a company in Luden, Germany, who makes a machine that has a very different approach. Through very precise metering of the gases used and the pressures within the chamber, we get a very consistent result. So let's talk about the process. The process is straightforward. It's straight up physics. A very, very high temperature flash of heat is what's used to deburr the parts. So the way it works is we put the parts in a chamber, and that chamber is sealed with 600 tons of force. We then pressurize the chamber, varying pressures depending on the material, with a mixture of methane and oxygen. Then comes the fun part. We light it. And the resulting flash is 6,000 degrees for 20 milliseconds. That heat has to go somewhere. And where that heat goes is into all the thin edges on the parts, the burrs. The burrs then oxidize immediately, meaning they disappear, they're gone. Now, when we're running aluminum, that's all there is to it. It's over at that point. Part comes out real hot, but it's deburred. When we're running iron, and this is where we get into a problem in the United States with how we apply thermal deburring. When we're using iron, the byproduct of that first flash is iron oxide. Yep, rust. Rust is not good. So historically, in the United States, on iron product, if it's thermally deburred, it goes from the chamber to an acid bath. Now that's bad on a bunch of reasons, but the first is it's bad for our employees. It's bad for the environment. It's also bad for the dimensions on the part because it actually eats away at the metal as much as the rust, and you can change your sizes. So in Europe, they were forced to develop a better process because the acid's not allowed. So what they came up with is on iron parts or ferrous parts, they do a second flash. This is a stoichiometric mixture of gas, so it's slightly different. It's at a slightly lower pressure, and the flash generates a different result. The result is it knocks the iron out of the iron oxide, and you come out with a part that's black. Still not usable as is, but now we can wash it off with an aqueous method. And when we're done, the part looks better than when it went into thermal. The gas never forgets to go down a hole, so we never miss a burr, making us an invaluable supplier for hydraulic manifolds.